Economics 53, we're about to move into the modeling section of the course, and this is an introduction to macroeconomic models. I decided to put this on video and video only so that I could focus in the in-class lectures on the actual three models we're going to be looking at: the aggregate supply, aggregate demand model, the loanable funds model, and then a computer simulation model of the macroeconomy. Now, before you look at this video, please first read Chapter 1, entitled Economic Models. That's in the course outline, and there's the link right here in the video if you don't have the course outline nearby. And this is meant to be just a supplemental reminder of that comment, kind of an overview and a commentary on it. It's mostly the chapter that I want you to rely upon. So let's start this, and I'll try to move through it rather quickly. First of all, there's going to be 4 general classes of economic models that we'll be using in this class. The first is standard for introductory economics, visualization models, where you're trying to use a set of graphs or something to make a point about macroeconomic theory. Then usually underneath the visual models is some implied mathematics, and in some classes you can introduce the mathematics and use it to supplement the model. And then finally, there's an extension of the mathematical models that allow you to fit estimators so that you can state, for example, that the range of parameters possible for this variable or that variable is some value that is derived from some statistical analysis. And then finally, most useful, I think, in an introductory course are computer simulation models. And we have a pretty good model here written specifically for this class in Python called Macrosim 1, Macrosim 2, and BudSim. It's basically the same model, the 3 different applications. So let's say a little bit more about these 4 types of models. Now, first of all, you've seen the standard supply and demand model that's common in both macroeconomics and microeconomics. This model first appeared in 1890 in a publication by a famous economist named Alfred Marshall. The supply and demand model was meant to capture the sense in which the interests of 2 opposing parties, producers or suppliers who are trying to get the highest possible price for their product, and by buyers who are trying to buy the product at the lowest possible price, results in an equilibrium price that clears the market, normally represented here by where the supply and demand curves, as they're called, intersect. If you took any economics in high school, you saw this model. To be sure, this is used absolutely everywhere. And the one complaint that non-economists have about the model is it tends to switch the axes. The dependent variable ends up being sometimes on the bottom, and the independent variable ends up being on the upright axes. And so sometimes it doesn't look like the standard mapping you get from its underlying mathematical model. This kind of model is useful when you shock it by causing the supply and or demand curve to shift, producing a new equilibrium price and quantity about which you can say something. Now, a math model that might be used to underline this is this sort of elementary supply and demand model that has a new element called inflationary expectations. And I have that here just to show you that these models can be made as sophisticated as you want them to be. When we look at this, you can see that these are linear equations, and that results in the linear mapping we saw on the previous slide. But these don't have to be linear. They can be log linear or nonlinear in some other way. Normally, in an introductory course for supply and demand, they start out with the assumption of linearity because for students without a math background, even that is kind of hard to explain. But we can modify it considerably. This model has a solution represented here as equation 4. It just reduces to that equation, and that means that when you have supply and demand conditions that are understandable and explainable, that there will often be, or typically is, a market clearing price that clears the market. And once you know the price, then equation 5 tells you the level of output or market clearing quantity that we're going to see. Now, this example is a supply curve that is sensitive to the price, And the value of the B coefficient is therefore going to be negative, because if we go back and take a look at the supply curve is positive, the demand curve is going to be negative. When we go back and take a look at the demand curve, we see it has a slope that is clearly negative. And so that is actually shown here with a minus sign, and that is meant to indicate that the P is always going to be a negative value. Maybe not the best way to represent this. But we're also, in this case, shocking the demand curve a little bit by adding a new variable. We can see that the demand is equal to a constant term, then the adjustment for price, which has a negative coefficient. And then we can say there's another variable, it has a coefficient small e, referred to as inflationary expectations. And that might be a variable that has a positive relationship with demand, such that if, for example, inflationary expectations rises, we expect demand in response to rise with it. And so E has a positive value. In this context, inflationary expectations represents the notion by consumers that inflation is imminent, that prices are going to rise, that that's highly likely. And so therefore the suggestion is when we add such a variable to the model, that we're going to change our behavior accordingly because of the formation of these inflationary expectations. So once again, we have a clearing equilibrium where supply is equal to demand, and that gives us it's going to be at the same quantity. And then again, we have a price solution, and we have the quantity solution that arises from the price solution. So we have a singular market clearing model. Now, although we don't use them much in this class, you can take models like this and ask the question, well, what are your best estimates of the values of these coefficients? Such as, what is the best estimate of the value B if you're talking about, let us say, electric cars? And what is the sensitivity of the D coefficient when you talk about the demand for electric cars? Is it high or is it low? And if you've had a course in microeconomics, you realize that sometimes these questions can be converted to questions about elasticities of demand and elasticities of supply. That's a rather common application in not macro, but microeconomic behavior. So when you go and try to estimate the values of these parameters using statistics, using, for example, regression analysis, then when you come up with these values, you can say something considerably more positive about what you expect the market clearing price to be. So we take a math model perhaps and estimate the coefficient values statistically. Now in macroeconomics we don't really do that. That's a common practice in more advanced microeconomic theory classes. But what we do instead is construct a simulation model. Now this slide is complicated, and I'm not going to explain this specific simulation model in the slide. I'm just going to tell you here that a simulation model looks something like this. And this is going to be the Macrosim1 model that we'll end up using in the class considerably. So normally it has an identity at the top where we say national output, or GDP, is equal to the sum of the three categories of spending: consumption, investment, and government spending. And here this is a closed economy, so in this version of the model we're leaving out net exports. Then we have a consumption function. That's a function of disposable income. Disposable income has a definition. We define a budget deficit in equation 4, and we define some savings identities in equation 5a and equation 5b. Again, I don't expect you to know this model now. This model we will introduce in about 2 weeks from when this slide was posted, or when this video was posted, and you'll understand it then. The point is merely here that you can take these kinds of models, whether linear or nonlinear, and blend them together and actually run simulations based upon your assumptions of the coefficients. Here's an example of the output of Macrosim1, where we're assuming certain values for all of these intercepts, and A and B and T, the tax rate, and the like. And here are some policy variables that we will control, such as the money supply change, the level of government spending, and the tax rate. And then from that, we plug all of those in, run the simulation, and you get simulation results that tell you what the level of gross domestic product is based upon the assumptions you've made. So a simulation model allows for sensitivity analysis, where you can, for example, run a simulation where you assume the money supply growth rate is 5%. And you ask yourself the question, what effect does that have upon the growth rate of national output? Then after doing that, you can change the money supply growth rate to 6% or 4% to see what effect that change had upon the same level upon the new level, I should say, of gross domestic product. So simulation models are very useful to represent the actual complexity of the American economy and allow you to get some sensitivity analysis for policy variables. How big should we increase the money supply or the credit supply? What should the tax rate be if we want to reduce or eliminate the budget deficit? Or if we drop the tax rate and it results in a new budget deficit, how large is that deficit going to be? Questions like that. Now, a couple more things need to be said about the nature of these models. Many of these models, like the standard supply and demand model, and the first two models we're looking at, the aggregate supply, aggregate demand model, and the loanable funds model, are examples of comparative statics models. And the comparative statics models are very common in economics. They're popular because they eliminate the complexity of time. You realize in a real market where you're trying to evaluate the price effects of electric vehicles or what impact raising the money supply would have upon the interest rate, that this will happen over time in the real world. But time is hard to model. You have to use difference equations or differential equations, and those are hard to develop, to explain them to students, and they become very complex very easily. So an alternative is a comparative statics model, and it works the following way. You assume that a model is in equilibrium at the start, and that's kind of represented here by point A, where you have an established supply curve and an established demand curve, and you say there is a market clearing price that's represented as price 1 associated with level of output Q1. So then you ask yourself the question, what happens if there is a surge in inflationary expectations in the economy? And so that, of course, would take place over time, but you ignore that in the context of a comparative statics model. You simply shift out the demand curve to what you presume will be a new equilibrium, and then you reevaluate the price and quantity combination or the dependent variable combination, depending on the kind of model you have, that is based upon that exogenous shock. And so it's sort of like taking a photograph just before the shock and then a photograph after the shock has been registered. That's the sense in which it's static and comparative. You say, okay, this is situation A prior to the shock. Now that the shock has happened, this is equilibrium B that is the result of the shock. What can we say about the effect of the shock upon the price and level of output? So comparative statics models sort of finesse the issue of time and how it takes a while for things to roll out by simply taking a snapshot at the beginning, allowing the shock, and then taking a snapshot after the shock has transpired. A dynamic model allows you to avoid that, and we use a very elementary one in this class just to show you what it looks like. And in fact, the simulation models that we use can be turned into dynamic models. An example of a dynamic model is a very elementary difference equation model. This one shown here is an actual model. It's called the multiplier accelerator interaction model. It, as you can see, shows our consumption identity at the top. We're leaving out government spending in this version of it. And we still have a consumption function, but you can see that consumption at times t is a function of income earned in the previous period, income at times t minus 1. And investment is going to be equal to some coefficient times the spread between yt minus 2 and yt minus 1. I'm not going to justify this model here. Again, we're just using it as an example of what an elementary difference equation model looks like. I'm just pointing out that such models exist, and you'll see a couple of them represented in the simulation models. So you can represent time somewhat crudely through the use of difference equations or even differential equations, and we want to acknowledge that you can. Now, there's a few more things we need to understand. When you take a look at the linear model, in its simplicity, sometimes underneath that model is quite a bit more complexity than we realize. First of all, when you set up a supply and demand model, you're supposed to evaluate the factors that affect demand and the factors that affect supply. And both are influenced by the price. This negative sign here means that for the demand curve, that relationship is inverse. The higher the price, the lower the level of demand. The supply curve suggests the opposite for producers. The higher the price, the higher the level of output. But we also say in the macroeconomy that demand is influenced by our income, by our wealth, and those are related but not the same thing. If it's a general economic model for the whole macroeconomy, the size of the population might matter. And we can have economic and business variables in here too, if we want to represent them. Here's an example of where we say advertising actually influences demand by increasing demand. If you've had microeconomics, you know that substitute prices can influence demand, which is to say the price of a internal combustion engine car is going to affect to some extent the demand of an electric vehicle and vice versa. But also we're saying that inflationary expectations can affect demand. And the plus and minus means that we have an a priori reason to believe that if there's a rise in income, it shifts the demand curve positively. And that's in fact true of all these variables. An increase in income or wealth or population has the effect of shifting the demand curve out, and any decrease in any of those variables would have the effect of shifting the demand curve back in. So if, for example, inflationary expectations were to abate, then that would have a tendency to pull the demand curve back toward the axis to some extent. Now, normally in the macroeconomic supply side of the equation, anything affecting cost is going to affect the supply curve. And so if labor costs rise, resource costs rise, advertising costs rise, those tend to have a contracting effect upon the supply curve. And if for some reason those costs are going down, it has an expansionary effect upon the supply curve. So the whole point of this slide is to make sure you understand that even when you're using a very elementary looking comparative statics supply and demand curve, that underneath it may be more complex mathematics that's causing the supply curve and the demand curve to shift in the interim between the two equilibrium points when you move from A to B. Furthermore, we're also implying that these all have a math equivalent, and you can represent it as a series of equations. So you can present it at any level you want. Just graphical and leave it there, but remind people that there is some sensitivity of the model to income and wealth and inflationary expectations and other expectations. Or we can say, look, we have a demand curve that is in fact a function of all of those variables that we talked about, including some that are common to both, such as the price, but also income, wealth, and so forth. And we have a supply curve that is a function of a long list of similar but also other variables. The x and y vectors here in this notation means that we can add just as many quarks to this thing as we want, depending upon our complexity of the model. We are not necessarily implying that the relationship here is linear either, even though in the visual models they typically are drawn that way, if for no other reason that it's easier to draw them that way than it is as nonlinear. The implication, though, in going back to the previous slide, is if here we're saying that the sensitivity is positive or negative, but in this case, for example, positive everywhere, but on the cost side or supply side, negative everywhere, then that implies in these functional relationships, however represented, that the first partial derivative of demand with respect to its component is greater than zero if that sign is positive and less than zero if that sign is negative. And the same thing is true for supply. We're saying, therefore, that the quantity supplied by producers with respect to the cost of labor, for example, that sign is negative. So if the cost of labor rises, the quantity supplied will fall in result. So when we build the model, when we build the aggregate supply, aggregate demand, and the loanable funds model, then this kind of structure with these implied relationships here mathematically are built into the model. And you'll see that application when we come to them. Now there's one more thing we want to talk about here, and that is in these models there is a presumed tendency toward equilibrium, which is inherent in the models. There's supposed to be over time a price-seeking function of these markets that make the markets more efficient. And normally the model suggests that if there is a price in operation that is no longer the equilibrium market clearing price, such as for whatever it is we're representing here, $600, if that price is too high, as is shown here, then you can tell that the quantity demanded represented by B, which is only, say, 8 million, is far less than the quantity being supplied, which is represented by A, which may be, say, 14 million. And so, therefore, when the price in a market is too high, it shows up as some sort of economic signal that tells producers, at least, that they have to do something in reaction to the signal. Now, in this case, the signal in this elementary example is a clear inventory buildup. And so the producer knows that they're pricing too high, and they therefore have to lower the price, and they have to lower their level of output to ensure that they begin to clear out their inventory. It's not being suggested that this is a one-step process. In fact, it's suggested that this is a dynamic process that oscillates all around the market clearing equilibrium price almost into perpetuity, because these supply and demand curves are also shifting over time while you're still trying to find the equilibria from the last location. Sometimes the models that are used to show this are called cobweb models, because if you were to map out the price discovery process, it would be oscillating around the equilibrium all of the time and trying to converge to it, but perhaps never quite getting there. And so it's argued that markets have these systems of signals and penalties that cause the markets to move automatically toward a market clearing equilibrium. And to some extent that's an imperfection, but over time, of course, it means largely that the markets are relatively stable. And that's implied in the models we use that are about to come up. Now, for the reading and for purposes of the examination, I want to make sure that you understand these following concepts, because aside from this, I don't talk about them at all in the class. I go straight into the models. I go to some pains to talk not only about expectations enhanced models and why they're so robust, because you don't understand much about modern economics unless you understand the role played by expectations. But specifically, I want you to know the difference between adaptive expectations and rational expectations, and I want you to understand that difference based upon what is written in the text, because I'm not likely to spend much time covering it in the actual lecture. In that chapter, I talk about the primary limitations of these models, and of course they're pretty easy to state. The functional form is very limiting sometimes, like if you're using a linear model, well, the world's not linear. You have a limited number of variables that you can use in a world where there's a very large number of variables that actually affect the value of things, and we know that. There's even the issue of whether the model's solvable, and when you make it complex enough to represent the real world, they become difficult to solve. And things like that are discussed in the text, and so I'll ask you some light-weighted questions about the limitations of models. And the one thing that I really try to make clear in this class is students sometimes take microeconomics and they see these supply and demand models and they imagine that business managers somewhere are using these kinds of models to set price, or that they're applied models or pragmatic models, when in fact they typically are not. These are meant to be models that help to understand conceptually the way a free market economy works by sort of giving you an idealized image of how that market moves toward an equilibrium or finds a price. They are not meant to be applied models. Nobody uses a supply and demand model to set the price for the new Ford Mustang electric vehicle. The managers are going to have to guess that proper price based upon their knowledge of these markets and the cost of making that vehicle and a whole bunch of other things as well. And there are efforts to estimate demand curves and demand elasticities, and sometimes those go into making decisions, but sometimes decisions are made without that. Do you think the Panamanian coffee producers who grow the coffee that I drink are sitting down there somewhere in Panama with supply and demand curves trying to figure out how to price their coffee? They have to take the price that's settled by the co-op, and the co-op doesn't use supply and demand curves either. So the model exists as a template to sort of say, in a very ideal sense and an over-idealized sense to some extent, this is kind of how the mechanics of a market economy actually work. It's meant to be explanatory and conceptual and not pragmatic and useful. And of course, to the extent that I provide examples, especially about inflationary expectations in that chapter, you need to try to remember them, because that's where I'm going to ask you questions for the examination. The examination coming up is really going to stress questions arising from the aggregate supply, aggregate demand models, and the loanable funds model, and the like. But nonetheless, the sort of simple examples used in the first modeling chapter on which this video is based will end up with at least light-weighted questions in that as well. So I hope now that this prepares you to understand the aggregate supply, aggregate demand model, because you can, the next thing you can hear from me in the actual lecture is a discussion of that model without this. I might add, by the way, as a footnote, that it is not important that you hear this before you hear that model. It's just at some point I'm hoping you have a chance to view this, because it gives you, once again, kind of an oversight, but the timing of it isn't all that critical. All right. Very possibly you've already seen the aggregate supply, aggregate demand model. If not, that's coming in the classroom next. I can never figure out how to shut this video off, and we're done. Yes.